Okay, now let's talk some more about ozone. So what is our ozone layer and what is happening to it when we talk about holes in the ozone layer? Okay, so ozone in the upper atmosphere, it's constantly being created and consumed. There's something called the Chapman cycle that explains this process. And so every day, ozone forms and then a whole bunch of stuff decomposes. So this is the Chapman cycle. It was proposed in 1930, and it is formed and maintained by 4 chemical reactions. So UVC comes in, it breaks bonds in an O2 molecule. It splits apart. We get 2 radicals. So that's where there's an unpaired electron floating around. And then those radicals, one of them bumps into an O2 molecule. An O2 molecule bumps into or turns into ozone, and then UVB comes in, it disrupts the bonds in ozone, and then that breaks up into oxygen and an oxygen radical, and then the oxygen bumps into another oxygen radical, and so we get this whole cycle that continues. Okay. All right, now, how do we know how much we have up there? So we can measure this in something called Dobson units. And so we're able to take a look at that by looking at a column that we can measure. Okay, so we look at this ozone concentration down at the South Pole. All right, blue curve on this graph here is typical altitude profile of ozone that shows no depletion. And then we can look at it again and see that at this location, we've had severe depletion of the ozone layer because we get those near zero values between the 14 and 20 kilometer marks. All right, so our ozone hole, this region over Antarctica, and so we get a lot less ozone there because things are happening that cause us to deplete our ozone layer. So we have measured this hole in the ozone layer over many, many years. So this goes into, I think, about 2013 or so. And so we can see what has happened to our ozone layer over that time. All right, so how is it being destroyed? So there's water vapor and the products from that. There's nitrogen monoxide that's in the stratosphere. So, and then some of that nitrogen monoxide is also man-made. And then we have our non-natural causes, our man-made NOx compounds, so nitrogen with various different numbers of oxygens, and then a whole bunch of different ozone-depleting substances. So water vapor, what's happening here? Water reacts with ultraviolet light, produces highly reactive radicals. You get water plus a UV photon, splits into a hydrogen and a hydroxide radical. Participate in other reactions that break down the ozone and create more free radicals. So free radicals, they're very destructive. Remember, things want to complete their octet, or in the case of hydrogen, their duet. And so when you have that single unpaired electron hanging around, atoms don't like that. And so they're very reactive. They cause chain reactions. Lots of stuff happens. With our NOx compounds, all right, we get natural nitrogen monoxide forms from dinitrogen monoxide that microorganisms produce. And then man-made nitrogen monoxide we get from nitrogen and oxygen with energy. And so nitrogen monoxide is a free radical. There's no way to draw a Lewis structure of it without having an unpaired electron, because if I take nitrogen with 5 electrons and then 6 electrons from oxygen, I get 11 electrons. That's an odd number. There's no way to avoid having an unpaired electron in nitrogen monoxide, so it is a free radical. Then there's a whole bunch of substances that are classified as ODS, ozone depleting substances. So the characteristics of these, they are going to potentially deplete the ozone layer. They usually contain chlorine or bromine atoms, and they have a long atmospheric life. And this is critical, okay? This long atmospheric life. Okay. And so a lot of those, we get chlorofluorocarbons, halons, bromochlorofluorocarbons, carbon tetrachloride, methyl chloroform, hydrochlorofluorocarbons, hydrobromofluorocarbons, bromochloromethane, methyl bromide, all sorts of these chlorine and bromine containing compounds. Okay, so where are they coming from? Refrigerants, fire extinguishers, fumigants, pesticides, solvents, propellants, air conditioning systems, all sorts of different things. One of the supplemental videos from the American Chemical Society I have for you talks about air conditioning systems. So, lots of different places. So this one right here, this is an important one too. So we used to use these CFCs very, very, very extensively in our vehicles. And so I remember, like, if your AC went out in your car, you could go get it recharged with these CFCs. And so now these are way more highly regulated because they stick around in the atmosphere. We don't want CFCs getting up into the atmosphere because they deplete our ozone layer. Okay, so our chlorofluorocarbons, two of the most common CFCs. So chlorofluorocarbon, C, chloro, F, fluoro, C, carbon. Freon, so this is what was in car AC systems. This is Freon stuff. So Freon 11 and Freon 12. And so these guys, pretty gnarly to our atmosphere. So why did we use them? Well, first we didn't know that they were gnarly to the atmosphere, but they were stable, non-toxic, non-flammable, low boiling point, cheap, widely available. And previous attempts at refrigerants didn't have all of those characteristics. Some of them broke down. Some of them were very flammable. So these were super attractive. There are a lot of reasons why we wanted to use these CFCs. But when we look at chlorine, okay, so chlorine depletes our ozone layer. We get chlorine from CFCs, interacts with ozone, forming this chlorine monoxide and oxygen. And then we get the chlorine monoxide, we get this chlorine peroxide, and then sunlight breaks that down, which frees up the chlorine peroxide into free chlorine atoms and oxygen, and it keeps continuing the cycle over and over again. Every time that chlorine atom is generated, then it bumps into another ozone, and so the cycle continues and continues and continues. Okay, so where do we get the chlorine in the stratosphere that messes with the ozone layer? And most of that is from human activity. So 75 to 85% of that is CFCs. There's a little bit from methyl chloride, and then a little bit from explosive volcanoes. So not a whole lot, but every once in a while a volcano will explode with such force that we do get some chlorine up in the stratosphere. And so when I look at the relationship between ozone depletion and chlorine in the stratosphere, well, ozone goes way down and stratospheric chlorine goes way up. So this stuff is really bad to have in our atmosphere. And so what happens? Well, when we get depletion of the ozone layer, well, we get more UVB radiation coming down, and so we get damage to human DNA. Plants and trees, they start to show an effect. Aquatic organisms, as I was mentioning, that we see marine life affected by our UV radiation. Okay. And then we end up getting degradation of a lot of things. Paint, rubber, wood, etc. And then more smog as we get that ground level ozone as a pollutant. So lots of things happen when we deplete our ozone layer. Okay. Now, why do we see it down in Antarctica? So a couple of things. Well, one, we get these ozone depleting gases all over, and you would not think that Antarctica would have a high concentration of things like CFCs because Antarctica is not densely populated. So why do we see the hole? And I put hole in quotation marks because it's a thinning of the ozone layer. It's not a true complete hole because everything's moving around. It's not like you're going to have a barrier where the ozone just stops. It's going to be a thinning out of it. Okay. Well, we get what's called an polar vortex. So during the winter, we get this polar vortex. And so the atmosphere, it's isolated from the rest of the southern hemisphere. Interior temperatures plummet and we get super, super cold temperatures. Okay. All right. So then what happens? Well, we get these polar stratospheric clouds. Okay. And so these clouds form in these altitudes between 20 and 30 kilometers when temperatures drop a lot. And so they play a role in our ozone destruction. And so they contain sulfuric acid, nitric acid, and we get all of these crazy reactions that happen in those stratospheric clouds. And so when our temperatures plummet, we get this stuff happening. Okay. And then over Antarctica, we also have things that are happening in the darkness. So we've got that nitric acid, we've got activation of chlorine all happening in that super cold air. And then as it comes out of winter and the UV radiation starts to hit again, now we're starting to form a lot of those other compounds. And so here you can see this. Okay, that's indicating that we've got that radiation coming in again. And then we start seeing depletion of the ozone layer, and it's a catalyzed reaction. Something forms and it keeps forming, and it's in that cycle there.